Hello. Hello.
Hello,
Good
sir.
evening,
Yes.
everyone.
Good evening, sir.
Good evening. So, um, today we'll do week 8. So, if you do you have any question in week 7?
Sir, I have posted a question on forum regarding the um, that parameters like of convolutional neural networks. I'm not getting the strides are given and pooling layers is given. That formula
Okay.
I'm confused.
I'll explain that. So, we'll,
Also,
okay.
sir, please explain the back propagation within
Okay.
a layer because it is very.
Okay. Uh, okay, we can start that. So, I'll do that convolution. Let's start. Let's start from. So, this is lecture on CNN. We'll cover that. Okay. So, in CNN, this is uh, what convolution neural network, right? So what we have is, let's say we have image, right? So I have image. So image is some uh, some kind of matrix, right? So let's say if it's a grayscale image, that will be only one metric like this, okay? 2D metric. So only one 2D metric will be there in grayscale image. And it has some value. So grayscale image is being decided like so whatever value here will come up as like will be between 0 to 255. Now sometimes you might have seen some different kind of combinations, you know, like 0 to 64 or 0 to maybe 8 or something. So anything, these all are possible uh, ways to create a grayscale image. Uh, okay, so 0 means there is no color there, which is being represented as dark, like 0. Like, so it's like black color, like dark. There is nothing. And max, whatever that max is, 255, 64, 128, anything is fine. You can choose that. That is being represented as white. And then in between all the grays will be there. Okay. So something like that image is being formed. So here a color is being put at it. So some values will be there like 8, 4, anything, 250. Okay. And if it is 0 to 250 values, that something like that values will be there. That's how image is being formed. Okay. So this is our images. Now, what we uh, need to do is we need something which is called filter, which can extract the features of uh, of an image. That's what we require from a filter. So filter is something we use which should be in a smaller size than the image. Otherwise, uh, there's no difference, right? So something of smaller size we'll use most likely. That's what we'll do, right? And it is also some kind of matrix, two cross, some kind of 2D matrix. Okay, that's what filter will use as of now. We'll see what we'll do if there is RGB. So another form of image could be RGB. So RGB is like you have three channels like this, right? So let's say R, G, and B. Same thing like here it was. It is a matrix of R, matrix of G, and matrix of B. All of them were concatenated, right? So let's say R was a 64 cross 64 image. Then G was also 64 cross 64, B also. So the total size of this image will be like this: 64 cross 64 cross 3, right? Something like that. So this is how RGB images. So let's say as of now, we have let's imagine we have a image, a grayscale image, okay, uh, which is of, let's say, 4 cross 4, something like this. Okay, so this is the image. Now let's say I use a uh, filter of 2 cross 2. So what we are doing is what we can do with 2 cross 2 is we can do 2D convolution. Now let's say if this is the uh, image, kind of like it's a straight uh, vector, and there is a filter of this size, that is a 1D convolution. Okay? 1D convolution. Now another possibility is 3D convolution is also possible. So let's say if your image is like this, okay, and your filter, so this image is of 3D, okay, image is of 3D and filter is 2D. Then you need to go, so you need to extract extract features from here. Then you'll go here, then you'll go here also, right? Something like that. So if you do that, uh, that is called 3D convolution. So filter is 2D, but this is called 3D convolution. Okay. Now we'll see what we'll do RGB later on, but as of now, we'll continue this, that we have a 4 cross 4 image. Uh, I have something like this, let's say, and let's say I have filter of 2 cross 2, 2 cross 2 filter. Now I'll put here that filter. So I want to extract features out of it. So how will I do it? I'll put my filter here. Okay. And let's say the values here are, let's say, x11, x12, then uh, say x11, x12, x21, x22. Okay. Uh, Forget about this as of now. Okay. So this 4 values are there, and here let's say values are f11, f12, f21, and f22. Right. So something like so. So what we'll do is we'll produce an output which will be like x11 multiplied by f11. So this value get multiplied here. Similarly, this will get multiplied here. This third one and this fourth one. Okay, so something like this, and then summation of that. X22 f22. Right. So this is uh, one convolution. One convolution happened here. Now we have to do that for all the pixels in the image. So what we can do is we can use some stride, that I want to move by this step size. So stride is kind of step size. How much step size you want. So let's say one is step size, then I'm going to move from here to here. This is my one step size. Okay. Then I'm going to move there. Right. So this part. So I'll move if I move three. If I have step size one, then how many times I'm going to move? 3 times, right? So from here to here, then here. So something like that we can. So so each stride will produce one output, right? So let's say first convolution happened and it produced one output. Then second convolution will happen, it will produce another, and third, so on, right? So we are going to put all of them in a matrix. Now what this matrix size is going to be, you can do like that. Let's say here if I move one, then how much width of output I'm going to get? 3, right? Output of 3 in uh, a width of that, right? And similarly, I'm going to move one down after this. So once I go like this, then I'll come here. and do this convolution, and then I'll go there. So I'll have another three and another three. So I'll what I'll get is 3 cross 3 image. Sorry, 3 cross 3 output after doing the convolution operation, right? So what will be the so how I'll know if I have, let's say, image of, let's say, 125 cross 125, and I apply a 3 cross 3 filter, okay, and my stride is, let's say, 2. Then what I'm going to do? Uh, so so the formula is something like you you wanted to which operation? No, you have to you have to do this operation only. So this is the operation of convolution.
So,
There is no
I
other.
have seen some filters like they take average value, some take max value. So is it that
That is that is not convolution. That is called match pooling or pooling. So there are this is convolution. Another kind of filters are which are pooling of are called pooling filters. Okay, so in this there is max pooling, average pooling, even median pooling is there. Whatever you can think of mathematically, all this mathematically, whatever you think of, that kind of pooling does exist.
and sir in
So
convolution we have to always take the dot product and
yes,
like okay sir.
yes. So convolution always happens like this. There is no other way to do it. You just multiply, add, and whatever value you get, you put it there. Okay. So okay. Now the initial question, like how will I determine the size of my matrix? Let's say I'll I'll add one more thing, which is padding, which is 0. So padding is uh, so let's say your initial image was something like this, right? So generally, what happens is we wanted to if I start from here, let's say if I start from not in this, but let's say if it is a 5 cross 5 image, and let's say if I have one, two, three. So let's say I have uh, 5 cross 5, and I have filter of 3 cross 3, right? So 3 cross 3 filter would be coming here first. So what is being assumed that the middle point is there, and around it one uh, all of the site one cell is there, and from that we are taking value, right? So if you apply uh, let's say uh, a filter for edge detection or something like that, right? So those filter will look like that. Kind of it requires to be of this type. So initially people started making this filters by uh, by thinking like how a mathematical operation will produce only features like edges or object detection, something like that, right? So those kind of filters were initially being uh, derived by researchers, that what kind of filter we can make. Then later on we decided why should we think what kind of filter will be there, or what kind of feature we are extracting. This is also a part of convolution neural. We can do back propagation, update the filter uh, as we go on, right? So that's what later on thought. So that's why if here I am, and there's one point around, like one cell around it, I can extract value. What if I wanted to extract value of this? How will I do that? So or uh, so so how will I do that? That is the idea. So what we can do is we can add a padding around it. So padding is just, you know, adding zeros around. So zeros, if you put around all of it, so it's like full not here, but uh, so everywhere you will put a 0, and so 0, 0, 0, 0, 0. So this is called padding. We did a padding of uh, size 1. So this is p equal to 1. If I do, then this is a padding. If I do another padding, p equal to 2, then there is another layer I'll add top of it. Okay, so 0, 0, something like this, all across, right? All the sides I have to add. That is called padding 2. So then I can actually start my 3 cross 3 filter from here, right? So if I start from here, uh, we think it should be here also. Then I can extract values like this. Okay. Something. So then I can start from here or here also, anything. So depends on what kind of padding. If padding equal to 1, then I can start here, and then I can extract this value. Okay. So something like so. Is it important? Do we wanted to miss it? We wanted to capture the edges of the image. Depends on that you wanted to add the paddings. Okay. So padding are uh, relative. Like, do you want it or not? Depends on. So this is how you can add the padding. So So let's say if this is the image of 125 cross 125 and 3 cross 3 is the filter size. If you use height equal to 2 and padding 0, then what kind of image size you are going to get? So it's like there is a formula for it. You have to take filter or image size. So image size is, let's say, W image or something you can take, minus whatever filter size is. Of course, width you have to take, and that. And usually there are square filters only, but if you maybe try with other kind of filters which are not square, then you have to take width and height. Then we add 2 times padding. So why 2 times padding? 2 times padding is because if I add one padding, then there is one I'm adding here and one here also, right? So width is increasing by 2. So that's why 2 times of padding I have to do. Then I have to divide by stride. Right? So whatever stride is, I have to divide by that, and I have to add 1 on top of that. So if I do that, then I'll get the width of my uh, output, whatever output I'm going to get, right? So let's say in our case, it is 125 minus filter was 3, and there was no padding. I'll divide it by 2, and I'll add 1. So this is 122 by 2, which is 61 plus 1, which is 62. So the output I'm going to get is of size 62. Okay. Now maybe you can try with a small case also. Let's say I have 5 cross 5 and I have a filter of 3 cross 3. Okay. Now how I'm going to what size I'm going to get? So say with formula if we go, then that should be 5 minus 3. Let's say no padding. So 0, and stride is 1. Let's say stride is 1 plus 1. So this is 2 plus 1, 3, right? And the reason is, let's say I start from here, right? So this is where I started my first pad. I kept it here. Then I'll move once more and then one more, right? So that's all. Like, now it's covered. So my end of this pad is here. Okay. So 3 I got from that. Okay, width of that. Then if I wanted to move down, so from here I'll move here, then here. So end of my pad is here now. Okay, so this pad has reached here. So that's all I can get, right? So 3 cross 3 output I'm going to get, and that's what also we can see from the uh, formula also, right? Now let's say if I do padding of sorry, if I do, let's say, stride of 2, okay, stride of 2, then what's going to happen? So let's say initially I started here. Okay. So this is where I first put at my filter. Then I'm going to skip one and go there, right? So I skipped one and I reached here, and my end of this filter is here now. Okay, so I can't move further. So I can't move further. Now similarly, I'm here. Then I have to go down also like that. So I have to going to skip this row and move here. So that is what stride equal to is. then again I've reached here. So my output is going to be 2 cross 2. And that also we can figure out with formula that 5 minus 3, there is no padding. And my stride was 2 and plus 1, right? So this is 2 by 2, 1 plus 1 equal to 2. So this formula will give you what is the size output you are going to get using this convolution operation. Okay, the width and height you can calculate using this. So for the sake of it, I write that the output width is going to be width of image or input minus filter size plus 2 times padding divided by strides, and you're going to add you're going to add 1 on this. Okay, so this is how you'll get the formula for width, and same formula for height. Okay. So let's say h1 and same thing, right? So this is how you'll get width and height. Is there any question here? Any confusion? Okay. So let's say if I give you a question, let's say image is of 128 cross 128, and my stride or my filter is of 3 cross 3, and my stride is 2, and there is no padding. What will be the image size you are going to? What is the output size you are going to get? Any?
2 into 2 or 3 into 3?
It's 3 into 3. Filter is 3 into 3.
So 64 by into 64. Oh,
64.
you have given 264. Yes.
Filter size is 3 crosses. Stride is 2.
So I will minus it. So it will be 125. Okay, divided by 2. It will be 62.5. So it will I take the 63 plus 1, 64 into 64.
No. So
Sir, it
here,
should be 63, I guess, if I remember correctly. Because, like, while I was solving questions, even though it comes after dividing the value, it comes around 62.5. It's taken as 62, I guess. Like, we take the floor value, I guess.
yes, that is correct. So when
Not sure
you
why.
get a division, here you will take floor. The reason is just if you think like that, let's say if I start moving right side, and if there is no space, then I can't move, right? So something like that, and that's what happens. So 62.5 means there was no space ahead. So you have to reduce 1 from that. You can try manually that why it is 60, why it is floor and not ceiling, but that is the reason that you can't move forward. So here you are going to subtract this 0 and divide by 2. So 125 by 2, whatever comes up like 62.5, right? So we are going to take floor of that 62, and of course addition of 1 was always there. So the output you are going to get is 63. Uh, okay. Now, so that was that. Now, what we are doing in this course is, so we have this
So sir,
RGB.
so you have taken the floor and then don't add the plus 1, correct?
No, add the plus 1. Plus 1 has no. So formula is not changing anywhere.
Okay.
So when division comes up, you have to take the floor. So division is here. So plus 1 is outside of that. I mean, you can think of like if you take ceiling, then don't take plus 1. That is also good. But the formula is like this. So With division, you take floor. Okay, now we'll see how parameters are being calculated. So each filter, all of this filter uh, sizes. So let's say this is a filter. This is a 3 cross 3. So there are 9 filters in this. Okay, sorry, 9 parameters in this. Uh, Now let's say your filter is say like this. Okay, I mean uh, this is a 3D filter of let's say 4 cross 3 cross 2, anything, but I'm taking this. So how many parameters going to be? Parameters, that is 4 cross 3 cross 2. So that is 24. Okay. So all the values, all the values in a filter. So this is also a filter.
Sir,
It's a 3D filter.
is that not that filter size parameters is also dependent on the input values depth number of parameters? So if this
So
is
depth
added,
is there, no? Depth is 2.
no.
So
So I am adding this AF into 4 into 3 into 2 with the filter size. Now if it is added on the 100 into 100 into 3 images, then the size will be 72, na?
we will go there, but yeah. Okay. So let's say I have image of RGB. Uh, Now let's say RGB is like this. Okay, so there are 3 channels going to channel. So this everything is called channel R, G, and B. 3 channels are there. Let's say I have 128 cross 128 image. So this is my image. I'm using a filter. So now I have to use. So what we can do is, one way we can use 2D filter and move across this and then go on inside also. That is called 3D convolution. Okay. Another option is we use 3D filter. So what we are going to do is we are going to use some matrix, but it has a depth of 3. So depth of 3. Why 3? Because that many channels are there, or that much image depth is there. So I can use that and I can do 2D convolution. Okay, so these 2 options are there, and what we have done is we are going to use this. So this is what we use in the course, and this is what is being used in every bit. So this is the convolution operation being used by all of us, right? So now um, we have this 3 cross 3, and um, so let's say my uh, filter is 5 cross 5. That is this 2D matrix. It will have depth of 3 also. So it will be like 5 cross 5 cross 3 should I choose, because 3 is coming from here. You can kind of think of like why 3 only and not other. Whatever depth of my image is, that much depth I have to choose for my filter also. Okay. So 5 cross 5 crosses. So that many, all of this are a parameters. Okay. So that is 25 into 3, which is 75. 75 parameters will be there in this. Now bias is not coming into picture. So if you read it somewhere, bias may be there, but in this course we kind of ignore the bias always. But for your information, I can tell you that for each filter, so this is a filter, there will be one bias for this. Okay, doesn't matter what kind of filter it is, 2D, 1D, 3D, there is one bias for one filter. So as many filter, that many biases you have to add. If bias somewhere comes up, okay, it will not come up in this course, that's for sure. Uh, but if it comes up, so this is how a filter is being decided. Now, if I go to the part where there is, yeah, so lots of calculation of parameters is there. I will. So if you see the architectures, Yeah, this all we have covered. Now, yeah, so let's say I have this. Um, okay, let's say I have this. Now the image is 30 cross 32 cross 32. So this is a grayscale image. Okay, and I have stride one, 5 filters I've used. Sorry, filter size of 5 is what I've used. So 5 cross 5 filter is what. Uh, 5 cross 5, and 6 filters is being used. So yeah, so 2 ways you can do. One is you can have depth, and yeah, sorry. So so here there is no depth, right? So you can use a 2D filter. Uh, so initially there is no depth, so I'm using a 2D filter of 5 cross 5. But later on I'll discuss here. So 6 filters I can. So why use one filter, right? So the idea of using multiple filter is that, let's say, with one feature you can maybe extract edges. Another filter uh, you can maybe extract something else, like, let's say, uh, uh, some background or anything. So whatever this feature, 3 feature, 4 feature, 5 feature, 6, right? So 6, why you wanted to extract, why you only rest at one feature only, but you can have multiple features also you can extract, right? So that is the idea. That's why we use multiple features uh, metrics to extract multiple uh, kind of uh, features. Okay, so that is the idea. Now, here, if I so what will be the output size, right? So that we can decide 32 minus filter, which is 5, minus 2 into padding, which is 0, and stride is 1, and I'm going to add 1 on this, right? So 32 minus 5 is 27, and 128, right? So that's what you'll get, 28. And same will be the width of that. Now, since I applied 6 such filters, I'll get depth of 6. So I have concatenated 6 filters. So one filter output I got, another filter output I got, another, and so on, right? So I've concatenated like this to all 6 of them. So now my output size has become 28 cross 28 cross 6 cross 6, right? So that is a tensor. So now we are maybe started calling them tensors. So this is how a tensor will look like. Okay. Uh, so yeah, so we are here. Let's say, so how parameters being calculated, right? So let's say first filter was that, which was 5 cross 5. Uh, just assume that in this code we will always use square filters. Like there will be no rectangle or any other different shapes of filters. Nobody uses them. So square filters are what we will use. So 5 cross 5 coming from there, and such 6 filters I'm using, right? So using that, how many parameters are going to be there? 150, right? So that's why this 150 is coming in. That I'm using such 6 filters. And same here. So okay, now I'm using pooling. So pooling is another operation. So I'll explain what is pooling is. So let's say you have matrix of let's see, take another one. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Now let's say if I apply max pool and stride 2. So in this also I can do stride 2. So first I'll put my this max pooling layer here, and whatever maximum value is, I'm going to extract it. So that is 6, okay, in this first one. Then stride is 2. So from that I'm going to move here. here maximum value is 8. So that I will write. From there, I'll move here. So here maximum value is 14. And then again, the last one will be here. And that is 16. So 16 is my final output. So like this. So this is how I'm going to get a max pulling output. Now here, did I learn anything? Did I try to learn anything? No, I'm not learning here anything. So there is no features. There is no parameters associated here. So I'm not into learning here. What I'm doing is I'm applying max pooling out of this. The
Sir,
reason is
sir, I didn't get how you took this stride as 2 because you have taken only one step, right?
uh no, I took 2 steps. So if I would have taken one step, so initially say I was here, then one step is like this.
Okay, sir.
So 1, 2, 3, 6, 7. Then max would be 7. Okay, but I do 2 steps. That is green. Uh, so I'm not learning here, and I'm applying max pooling. So the reason of pooling layers is so one was to reduce the size of the image. So it will reduce image size, and it will actually extract the most important feature out. So it depends. Like sometimes we are using average pooling, sometimes we do max pooling. So here these are the features, and from these features, maybe we wanted to average out the features. Maybe we wanted to take maximum of that, something like that was required. So that's why this max pooling was introduced. Now here, of course, it will change the sizes, but it will not have any effect on parameters. So parameters will not be there. Okay. So here, if I calculate, then 28 is my input size, and filter size is 2, and there is no padding, and stride is also 1, right? So this is how I'll get 26, uh, 26 by 1. So I think there is a mistake. The stride should be 2. Then it will be 13 plus 1, 14, right? So 10 only it will become 14. There is a mistake. So it should be stride equal to 2. So 14 is what you'll get. And how many max pooling we can do? Can we do more than 6 max pooling? No. Okay. So just remember that whenever we do max pooling, we always do as many uh, filters we have earlier applied. So let's say I have 6 filters earlier. So that's what the depth is. So each this pink one will produce one max pool. Another pink will produce another max pool. Okay. So we'll never have max pooling more than that. So there will be you will never see that there are 6 here, but 7 max pooling were applied. That's how it doesn't work. Okay. So max pooling is of course like what we are doing is we are trying to find maximum out of this, right? So if there is no there, what maximum we are going to find? Anything, right? So here we can't do that more than whatever depth is. Okay? So that's how I got my 14 cross 14. Now if I go here, so I'll maybe clean up a little bit. Okay, so we are here now. So enter image and the right was 2 here. Now here what we are having is 14 input is going there, and I'm using 5 cross 5 filter. I'm not having any padding. I'm using stride 1 and this, so which will give me 9 plus 1 10, right? So that's what I'm getting, 10 cross 10. But how many depth I'm getting? So I'm using 16 such filters. Okay, so 16 such filters I'm applying. So that's why I'll have output size of 10 cross 10 into 16. So 16 will be depth of it. Okay. Now how many parameters will be there? So how many filters did I use? 5 cross 5 filters were there, and I use how many of them? First, like, is 5 cross 5 correct? Did I only use 5 cross 5 filter?
Sir, 16 also.
16 also. Okay, so 16 of this 5 cross 5 filters I used, right? That's what the 16 means. Now, but did I use 5 cross 5 filter, or did I use any different size of filter? Um,
Sir,
I
in
used,
the filling layer,
yeah,
it is 5 cross 5 only.
no, I used 5 cross 5 cross 6 size filter. So this is now, so here now it's coming that 2D convolution part which I explained, right? That uh, uh, that let's say I have image and I use 3D filter, then I can do 2D conversion. That's what we will do, right? So that's what we are doing. We are using a filter of 5 cross 5, and we are always using a depth of whatever previous here, whatever the depth was, we'll use that always, right? So now filter is looking like this, like 5 cross 5 and depth of 6. Okay. So that's why we can do 2D convolution. Okay. And for 2D convolution, if I do that, so my filter is not now. So here my filter was 2D, but here my filter is 3D, and such 16 filters I'm using. So that's why this all multiplication, if you do, I think it should come 2,400. This is 150. 150, 15 into 16 could be 24. Mm. This uh, could be. Sure. So we have 15 into 5 cross 5 cross 6 cross 50. It's, um, 5 cross 5 into 50. Yes, it is 2,400. Okay, so this is 2,400. That is correct. So I'm just checking what's the other thousand. Now, what we are doing next? We are again doing pooling layer. So maybe max pooling, average pooling, anything could be there. Uh, but what will be the output of after this? Like, what would be the output size? So, so now can you do this? Like, I mean, you're center of two. There was no padding, and stride is one, and something like this. So it should produce 9, but it is producing 5. So I guess here, so stride is 2, 8, 4 plus 1, 5. Right. So both the places stride is 2, just in case you can uh, correct that. Then there is no parameter here because what we're doing, we are just doing adding or averaging, something like that, but there is no learning or something like that we are doing. So the size of the final thing is 5 cross 5 and the filter is 16, right? So something like that. Yes, that is 400. So this will be 400. So this final thing is 400. Now due to using that, what we'll do, we'll flatten it. So this. So for this final thing, having 5 cross 5 cross 16 is the size of this. Now we are going to flatten it. So you are just flattening it, right? So all of them will be now. So let's say you have this tensor, you're going to make it as a vector. That's what flattening operation is. And flattening will have size of whatever the size of, right? So let's say L into W into D, whatever this, you're going to multiply that, and that would be the size of this. So LWD cross 1, okay, something like that. Now, so here we are getting 400, and I guess we have used 120 parameter here. So if you do that, then that will make it okay. So just in case, like let's say if we have 400 here, okay, and yeah, let's say the output is of size 120, okay, and this is 400. Then how many weights you will require to produce that? This is the weight set parameter. How many weights you will require if you wanted to make a 400 size output to 120?
400 cross 120.
Right. Yes. So we saw in ANN, right, that so this input is there. Each input will go to the each neuron, right? So let's say first, second, third, fourth, like that. So all 400 will go into first, then all 400 will go to second, and so on, right? So 400 going to all of them will be 120. So it looks like this is 48, then 1000, right? 48,000, I'm getting it. And I guess biases they have included. That is what bringing 120 more. Okay. So here the bias is also there. So earlier we ignored the biases, but here the bias is being included. Then 84 layer after that. So now there is 84 layer. So how many weights will be there here? 120 cross 80, right? Uh, Whatever this is. So maybe 96,000, and I guess 80 uh, they have rated, or is it incorrect? Oh, sorry, it should be 84. Then 124 would be 1000, 10,080. That is 10,080, and 80 you add on top of that, you'll get 10,000. Sorry, 84 you rate that, you'll get at 10,160. Then the last layer is 10 output, right? So you'll have another layer which has 10 neurons in it. So of course you'll get 84 into 10. So that is 840 and 10 more. So 850 due to that. So that's how you'll get this all the parameters. Okay, fine. Anywhere you have confusion in this? Can you do the calculation of parameters here? Output size, anything? Okay, can you do this? Any calculation is required here? Parameters, output size, uh, like anything, filter, how output is coming out, anything, everything is fine?
Yes, sir. Fine, sir.
Okay. So this is how you'll get a produce. So now you can try calculating for all of this architecture, right? So few architectures are going to be there. This lean at 5. Now let's say they use 30 cross 2, 32 image. Then they applied this convolution of 5 cross 5 filter. They use stride 1, and so on, right? So I guess here they have used stride 2. Okay. So the earlier architecture was of lean at 5. Then similarly there will be architecture of few more would be there. So ZF, AlexNet, ZFFnet. You don't need to remember this. There will be no question of how, what will be the size or what will be the architecture, something of AlexNet or something. But at least you should know what is there, how many layers are there in this. So layers are generally considered as parameter layer. How many parameters are or how many convolution networks are there, layers are there? That's what we consider layers in this. It might come somewhere in programming if you when you but you have to mention that. So here 4, 5. So that's how the naming will come later on, I guess. The name of VGG 13, VGG 16, and all right. So let's say if I go to VGG, because we are comparing the Alexa ZFnet here, but let's say VGG net, right? So now you see. Uh, so this is the final answer. So here, if you see, there are two convolution here, then 2, 4, then 7. It, 7 means I'm adding it. So 2, 2, 3, 3, 3, and then here 2. Uh, so 1 layers are here, right? So if you add all of them, so 4 plus 3, 7 plus 3, 10, 10 and then 13. Uh, 13 is there. So maybe this is this architecture of VGG. Uh, I'm sure this is this we don't include, but this should be VGG 13. Okay. So the naming of VGGs are coming from that term. So VGG 13 will have
Hello, sir. You are not audible.
yes. So just remember, try to uh, understand this architectures, all of this ResNet, GoogleNet, and something like that. So one more thing will come up with that is called inception module. So this is what an inception module will look like, something like this. Okay. So you apply 1 cross 1 filter and then 3 cross 3 filter, and then you have this, right? You concatenate them. So how will you concatenate them? You will apply padding around it. So 1 cross 1 will have so wherever you apply 3 cross 3 will have a smaller size. 1 cross 1 will have a little bit larger size, right? So output you are going to it because the formula is W minus F, right? So this F will reduce size. So this will have smaller, this will have larger. So how will you concatenate? You'll add that much padding, whatever padding is required, and then you concatenate. So that's what an inception module will look like. And this is what an inception module is. That's what used by GoogleNet to improve the scores. Okay. This is what this inception module is. Here you can see this inception module, something like this. And you go on, right? So whatever the calculations are, you can try that. You will be able to get that. Okay. So this is all in the understanding of architectures of this. Okay. Now we can do the back propagation part for the convolution. So for that I will do okay. can use this. Um, so what we discuss is uh, same thing, just clean. So okay, so what we discussed, we have input and we have filter. We apply convolution. Then if I do here, so let's say I put filter here, side one, another one, and like this, right? So that's how I get output of 4 size, 2 cross 2 size. Okay, so that's what we discussed as of now. Now, what is the output of a? Okay, so how does back propagation happens is, let's say some formula you have, like let's say a equal to w x plus b, something like that, right? So this w x and b contributed in the formula. So now if I take tau a by tau w, you know that the output is going to be x, and let's say a by x, then you know that the output is going to be w, and if I do with respect to b, then output is 1, right? So something like this. So if something has contributed in forward pass, then that only can contribute in backward pass. Otherwise, not possible. Okay. So so what is happening while we are doing uh, convolution operation is, so let's say this convolution happened, and uh, and let's say I got O11, right? So O11 is the first one. So you can remember O11, 2, 1 and 2, something like that, right? So this 4 input and this 4 filter in contributed this like this, right? Now, okay. Now what in back propagation I'm going to do is, either I'm going to uh, take derivative with respect to any element of x, let's say x11 or x12, x2122, any element of x, or another is I'm going to do similarly with f also, right? So f11. So this two kind of uh, derivation I'm going to do from the output, right? So this is the output. X11, F1, F1 to F1, so on, right? So something like that. So uh, yeah, yes. So this is what either this or that. There's two kind of thing I'm going to do in back propagation. Now let's say this just this equation. If I look O11, now if I tell you what is derivation of O11 with respect to, let's say, X11, what is going to be that? Uh, just this equation we look into. What is that going to be?
F1.
F11, right? And similarly, if I do with respect to X12, then I'm going to get F12. Okay? And so on. So this is what I'm going to get. Now, did X now let's say if I see the all 4 of the formulas, okay. Now where X11 has contributed, so here it did. Is anywhere it has contributed? No, right? So nothing, nowhere, anywhere else. Now, similarly, if I ask you about X12, where it has contributed, so X12 is here, right? X12 is here also. So that has contributed twice. So let's say if I do O11 uh, with respect to uh, X11, then X12, then once it will come there, F12, and and one more could be like O12, then that will contribute this thing, F1, something like that. So um, so now That's what we discussed, that let's say f is coming, x is coming, they are doing a convolution operation, output O is what you are producing. Fine. Now uh, uh, so so let's say by some chance that you have a derivation till O. So this O is also connected to something, right? Let's say uh, one could be, earlier we saw let's say LXNet architecture, that input is there, then we apply some convolution, then we apply some max pooling, another convolution, then max pooling, then we do flattening. So this is, let's say, flattening, right? We'll just call it that. And then we apply ANN architecture, some neural network and all, right? So neural network, and then another, then we produce a loss, right? So that's what we used to do in neural network. That this is there, then apply softmax and have loss. So now how am I going to do backpropagation from this? So let's say by some you can kind of expect that you know loss till here. So DL by this flat. Okay, this flattening, which is like the last single layer. Okay, you know the loss till there. Then how you can go back. Okay, so max pooling, I'll explain how you can do that. But let's just think that I have only convolution at the last from that. Then how can I do that? So they have actually explained. So if you do with F11, what is loss with F11? So let's say you will come to O11, right? Then O11 has F11 contribution. O12 has F11 contribution. O21 has F11 contribution. O22 also has contribution F11, right? You can check the formula. So this is a formula. So we're talking about F11. So it has contributed all four of them. Okay? All four of them it has contributed, and so all four of them will get updated, right? If I do a derivation of this, so you know that when we do derivation across multiple paths, we sum them, right? Multiple chain rule across multiple paths, we have to sum that. So that's what this formula is, that we are summing them across all the paths like that, right? So let's say you have this z square, you have z here, and then you're producing z cube here, and then it's a z and z cube are producing maybe loss or something, right? So something. So how you can do this? You can do z square and then z square with respect to z. So this is one path, okay, and another path is z cube, and then z cube we are going to do with respect to z. So that's why you can find out multiple paths and you have to sum them. That's how the gradient is being calculated. So that's what we are doing. We are going across multiple paths of F11. So wherever F11 has contributed, if I'm going to update the, or if I'm trying to find how much F I should change so that loss can affect, that's what I wanted to find, right? So I have to multiply this across each path, and then I have to sum the those paths. Okay, so that's what the summation will look like. Now, what is this actually what we are doing here is something like we are taking yeah, so loss with respect to filter will be like this, and in this part we can figure it out. So the component of that, and now what that actually is, if you uh, so if you wanted to find loss with respect to filter, then that is actually if you apply convolution of input with respect to whatever the gradient of loss you got it. So dl by do, that you can find, that you will have, right? So the last layer which I mentioned, that the last flattened layer, this loss, whatever value you got here, okay, the flattened layer loss, that you can use, uh, and you have input x. So some input x will be there, right? On top of that, we have applied this filter. So this filter was applied on some input. So that input and this output, so the output is something else, but this gradient, that if you do a convolution on that, you'll be able to figure this out. Now, similarly, if you wanted to do for the x, then you can see it is a little bit different. Now, x is not contributing everywhere because f was always contributing in each of the convolution operation, right? Because f is the one which we put on this, then we shift f, shift f, shift f. But x is sometimes available, sometimes it's not available to us. So we'll only be able to do when we do the operation, right? So it is like how you know how many times it comes in. It's like what are the filter sizes? So here it is 2. So this will contribute 2 times 0, which is 1. This will contribute 2 times 1. This will contribute 2 times 2. This is also 1. 2 times 0. Okay, so this many times it will contribute. So this many uh, should be there in the back propagation algorithm, right? Rated correct.
Sir, can you continue in the next class?
Continue next class. No, so there is one small thing that you need to understand is, I mean it's about to get complete. So this x11, x12, x13, 211. If you do all of this, you'll get this output. But what is that? That is a full convolution. The full convolution is what I'll just show you how it will look like. But that you will get it. So this back propagation is chain rule across multiple paths. But what you will get is something like this, right? Now I have nodes. So let's say you have this input and you apply ReLU on that. So we never talked about activation functions in this, right? But there is activation function also coming into picture. So whenever you apply convolution, after that convolution filter, we apply activation on top of that. Mostly ReLU, that's what we use. And then we apply pooling. And then let's say we do, so let's say some input was there. We apply some convolution. So you'll get some output, which is 4 cross 4. You apply ReLU on that. Then you apply pooling layer. So you get what is pooling output. Then you flatten it and you apply softmax on that. That is simple architecture you can see. Now, let's say input is of this size. This are the values of that. That's a mistake here. This output size should be 4 cross 4. It's a 44. Now, let's say this is my filter. Now, if I apply convolution, you get this. Okay, so this much you can do. If I apply ReLU, so ReLU, what will ReLU do is wherever it is less than 0, it will make it 0. Otherwise, whatever the value was. Now, just in case, remember that when we'll do back propagation from ReLU to something, right? So let's say ReLU and some input we have given, right? Now, when we'll do back propagation with respect to the input, how we do is wherever we have done this something, there will get 1 and rest will get 0, right? So this all will be 0. This all will be zeros. And here it will be 1. So that's what is, and here it will be 1 also while doing the back propagation. Okay. So just remember that this is how the mask, ReLU mask will look like. It will come later. Now the pooling will come up, right? So this is what you got after applying ReLU. Now if you apply pooling on that, now pooling, if so here you can see tie happened, right? So
Sir,
if tie happens,
how it came 2 in that ReLU? Sir, above the green one, yes, sir.
so this matrix, you apply ReLU on this, what you will get?
Okay, sir. I thought it's mask one. Okay, sir.
No, mask is something where, so wherever value was positive, when we do back propagation, you know that you will get like this, right? That if
Yes,
greater than 0, then uh,
it's
so it is a
one.
max of 0 comma x
Yes, sir.
respect to x, right? So you know the derivation of that. Okay. Now here tie happened, right? So what generally, let's say PyTorch will do is it will take whatever is the topmost, and then it will do the leftmost, right? So the top then left. So if there is confusion, always look for the first row, and that will be your answer. So this is how you get the max pooling output. Now you do the flattening of that, so it will look like uh, 1 2 1 1. Okay. So I have mentioned the transpose here. Now, okay. So let's say this was the flattened layer. Now on flattened layer, you have the flattened layer, right? Now you want to apply some kind of softmax or something you on this, and then you can predict the classes, or you can do the prediction, right? So let's say we have three classes, 0 1 2. Then I need to apply some this kind of uh, softmax activation layer, right? So whatever this 3 4 cross 3 something you got, and this is the output, and you do the uh, softmax over that, you will get this, and you can compute the loss like this, right? So this was the forward pass. We have done this the forward pass using that. Now how will you do backward pass? From loss, you'll go there, softmax, then fully connected layer, pooling, ReLU, and convolution layer, right? So that's how you know. With convolution layer, you can do both, right? So with respect to input and with respect to filter also. Now, why we wanted to do with respect to input is because input is the only one which will be connected to the previous layer if there was a layer. It's not there, but if just somewhere comes up, just remember that filter, sorry, input is the one which always contribute, which always connected to previous layer. So um, something here there is a mistake. Don't look into that. That is incorrect, but it should go like this. Okay, so you can multiply each of this term, and you will get this. This is uh, yeah, that is a mistake. Now we know that with respect to, so fully connected layer is this. Okay, and you apply this layer on top of that, and then you sorry, then you predicted the output, and then you have loss. So we know that we can directly skip the softmax part, and we can go here, just AL, right? So AL and HL kind of you can think. That we know that that derivation is going to be y hat minus y. We have done that, right? Or you might remember mine minus one hot encoder y minus y hat or something like that, right? So any way you can remember. So this is what we have to do, and then we comes to the layer, the fully connected layer, and now this will become little difficult to understand with uh, with just a discussion that we have this layer, and we have reached to the previous layer, right? Now how will you do with the input? Uh, so let's say A is equal to Wx plus B, right? Now what we are actually doing is we are doing tau A by the the input, right? So tau x. So we'll have this f t coming from there. Okay? Uh, don't worry, I'll share this with you if you don't understand, but you will get this flattened layer as output, and we will do this multiplication. So this is same as the last layer we used to do in the ANN part, right? So it's the same as that, right? So that's what we produce this output. You might remember this thing. It's just the F now. Earlier it was like H transpose or something, right? That's what H I minus one transpose, something like that was the name. But that is same. Now yeah, so wait, we did. Now input with respect to the if I do with respect to the X, right? So F and W. So there are two things. Now do I wanted to update this weights? Then I have to do this. If I don't want to update this weight and I want to move forward, I have to use this tau L by F, and it will produce W transpose in front and whatever this is. Okay. This matrix multiplication you will do, and you will have vector. Now see. So in pooling, after max pooling, we did the flattening of this. Okay. So whenever you do back propagation, you do deflattening of this. So whatever was that. So from 4 cross, sorry, 2 cross 2, you produce 4 cross 1. Now same way you are going to make the matrix uh, backside. Okay, so this deflattening you have to do, and something um, we did before max pull. So in max pulling, what we did is we had this 16 cross 16, right? 16 cross 16, and we end up having 4 cross, sorry, 2 cross 2, right? So wherever we have taken the pooling, so this element we have chosen this and this. That's where I'm going to put all these values back, right? So you can see that the red one which I have chosen, that's where I'm going to put back my values again of my gradients. Okay, so that's what you'll get from the yeah, from this. Okay, now I mentioned that whenever you do gradient of ReLU, you kind of having this mask kind of thing. Now you can multiply both of this mask and whatever output we got here, and you'll get something like this. So this is gradient with respect to the ReLU layer. And finally, we are at the convolution filter, which we initially started. So if I show you that we have done this part, now we are at the convolution. So we can do two things, either with the filter or with respect to input. So if it is filter, then I have to do the convolution operation of my input and whatever gradient I got, right? So this is my, you can take this as a filter, put it on this. So this is 6 cross 6. This is a 4 cross 4. And the output you are going to get is something like 3 cross 3. Okay? 6 minus 4, straight 1. Okay, there is no padding and 1. So if you do this, this is 3 cross 3. This is what you will get. But if you wanted to with respect to the input itself, so we had filter, we had input, and then convolution happened. So we are here, right? So dl by do. Now this part we have done. Now this part you want to do, that is called full convolution. You are going to rotate the w by 180 degree, right? So so initially this was looking like w was looking like this, right? So now I'm going to do 180-degree rotation of that. So 180 degree, so let's say 90-degree rotation is 1 1 1 0 0 0 minus 1 minus 1 minus 1, and 180 would be minus 1 minus 1 minus 1, and like this. Okay? So this is called 180-degree rotation. So that's what
But why we are rotating the filter by 180?
that answer is here. So if you wanted to do this operations of each of them, then you have to do that 180-degree rotation. So I'll leave it up to you to understand that, but the answer is here. Okay, so why we have to do that 180-degree rotation, so that the multiplication of this gradient. So you wanted to have this, right? DLO by F1 and something like this. So that's why we need to do that. Okay. So I was at the last part of this, that yeah. So we have to do that now. So this is the 180-degree rotation. Now we are going to do something called full convolution thing. So where what we do is we put here, okay, like this. Then I put here, and then I put here also. Then I put here also. Okay, something like this. So I have to kind of go out of this. So you can kind of think like I have to add a padding of size 2. So you can maybe add a padding of size 2 and do the padding and do the full convolution. Okay. So you don't have to stop. Even if it ends, you kind of add the padding of this and then you go ahead. Okay. So that is what full convolution will be, and you get finally this output. So you can see that the X has a size of 6 cross 6. So of course del L by del X also has a size of 6 cross 6, which we have. Okay. Yeah, so that's how full convolution, or that's how the back propagation in convolution neural network works. So the two things you have to understand is they are here. One is how with input you are getting this, which is very easy, which you know mathematically, and another is how you are going to get with respect to F, right? That here. Now each of them can be say that what you are actually doing is if you wanted to back propagation, you do this operations, convolution with input x and loss gradient, or full convolution of 180-degree rotate graph and loss of gradient. That is the same thing. So that operations what we wanted to try, we wanted to do for back propagation are kind of you can get from this part. This is the easier form of that. So that is that's all I have. So I'll share this example this PDF with you if you wanted to look into it. And this is another PDF where they explain what is the um, how backpropagation works. Uh, okay, any question? Um, any questions? Anything else?
Sir, where will you be sharing this PDF, sir?
I'll add it in the group, but I'll add in the course portal.
Okay, sir.
Okay,
Thank you.
I'll add it in the Okay, then if there is nothing else, we can stop.